Dr. Dr. Geetha ma'am is retired associate professor from Vijaya College, RV Road, Baswangudi, Bangalore, and she worked as a NCIEP coordinator in Indian Association of Physics Teachers. Also, she worked as a resource person in Physics Olympiad training camps. Apart from that, she worked as a faculty in Asian Physics Olympiad as well as International Physics Olympiad. Worked as secretary of IAPT Bengaluru and conducted many regional Olympiad exams. And she worked as a resource person at Talent Development Center, ISC Challakere, for high school and PUC teachers. They conducted some trainings. And she worked as a chairperson in BCU, UG examination, and she was a member of BOE and BOS. Presently, she is national coordinator for innovative experiments competition for the teachers. With this brief introduction, I welcome you once again, madam. Thank you very much for accepting our invitation and being with us today. The floor is yours, ma'am. You can start the session.
Thank you very much. And I'm very thankful to KSTA for giving me this opportunity uh, to share my thoughts about Bohr's atomic model. I am very happy to do that. And I want it to be more of interactive sessions. And if students, they can always, uh, since this is an online session, at the end, let us say that I will stop about 10 minutes before, so you can interact with me. I think that would be the better way, because you will have many questions and all those things. And in online sessions, in between might be little difficult for you, because I may not notice when you raise your hands and these type of things, since we will be sharing the screens and all those things. So let us have 10 minutes at the end. And, as with anything, this is all teaching should be interactive sessions. So, many of you in your school, colleges also, you might have studied. I think already that portion might be completed about Bohr's atomic model. So, why there was a need for Bohr's atomic model and all these things? So, let me start. Let me start with sharing my screen. So that would be best. Okay. So now this is the Bohr's atomic model that I would like to take up for today's topic. So why there was need for this? So these two are the most famous personalities, for starting Bohr's more so for atomic physics, and Rutherford more so for both. He is known as the father of both atomic and nuclear physics, because his one experiment, paved way for both atomic and nuclear physics. See, the beginning. See, this is actually not the beginning, because, when Dalton's atomic theory came, people thought that the smallest thing in this, in the smallest building block is an atom. It is indivisible. But what happened was J.J. Thomson, just I want to remind you that there are two Thomsons, J.J. Thomson and J.P. Thomson, father and son. Father J.J. Thomson got Nobel Prize for showing that electron is a particle, and his son J.P. Thomson got Nobel Prize for conducting an experiment to show that electron behaves as a wave as well. So father and son are very famous in this. So Thomson, what he did was his famous cathode ray tube experiment, in which he got what were known as the cathode rays. See, more about it you can learn in your books and all those things about this cathode ray experiment. So a high potential difference was applied for a gas under low pressure. And what he effectively did was he ionized some of the electrons which came out. He called them as cathode rays. So he noticed that they were negatively charged. And since atom as a whole is considered to be electrically neutral, then people understood that it has come from the atom. Therefore, there has to be that much of positive charge also in the remaining portion. So if negative charges have come out, means that means to say atom has both positive and negative charges equally. That is why it is neutral. So because of this high potential difference, these electrons have come out. Therefore, now there was need for uh, to so atomic models are required. So cathode rays had negative charge and very small mass. You can see that they were only 0.305 times the mass of the hydrogen. So this was the experiment. So all of you can see that high potential difference. So what he did was he imagined. See, all models, in your mind, something comes, how it can be, because we are unable to see it. Therefore, in your mind, so it is more or less like blind men, touching an elephant and thinking this is how the elephant should be. The ones who touch legs will think that it is they are like pillars and all those things. The same way, when whatever is coming out through that, he imagined what is known. Thomson himself did what is known as a plum pudding model. So he imagined that there is a positively charged porridge, and in that negatively charged raisins are there, so they are equal. And since the negative charged particles have come out, he imagined that the positive charges are quite heavy. Therefore, that pink portion is the heavier one. So he imagined atoms to be like that. And people knew that across the atomic dimensions are about 10 to the power of minus 10 meter, that is about an angstrom. Therefore, this is how he imagined it to be. But then, why this did not work? This will not work because Rutherford had two students, Geiger and Marsden. So Rutherford, a very great physicist, even though he got a Nobel Prize in chemistry, his work is very, very important everywhere. So what this Geiger Marston, he conceived an experiment. So for investigating the structure of matter, so he wanted to see that, somehow the for all the known phenomena, this was not giving, this plum pudding model was not giving the correct results. Therefore, what Rutherford, Geiger and Marston did under his guidance was that, from an alpha, at that time, alpha particle, people called it as alpha particle. Now we understand. Remember, we never knew what was an atom in the first place. Therefore, whatever rays were coming from the atoms, people had named it as alpha, beta, gamma, etc. Now we understand that alpha is actually the helium nuclei. That means from the helium atom, if you remove the two electrons, so then it will become helium nuclei. So it will be positively charged, two times positively charged. But at that time, they had called it as alpha particle. So there was an alpha particle because radioactivity was being studied simultaneously. So alpha emitters were there. Then it was the target was a gold foil. Why gold? Because gold is a very unique material in that it can be taken into very, very thin sheets of almost 1 atomic thickness. So it is highly malleable and ductile, which you have studied. So that is why gold is such a famous material. Therefore, he had taken a very thin sheet. So thin sheet means now you are practically, when you send an alpha ray, you will be practically you will be interacting with the atoms of gold. So that was the idea behind this experiment. And if at all, if they are scattered, then they can be caught by the microscope. This was the idea. So whatever angle, that microscope was capable of moving in a almost 360 degrees. So it was capable of. So it was catch. It would catch. So this was the idea. So this is what he had done. Now you can see that there is a video for this. All of you observe. This is a very beautiful experiment to show the alpha particle emitter. You can imagine that it is an alpha particle gun. This is the detection screen. So that is the gold foil. You can see that. So now for a better view. So this is an animation, how the experiment was done. Remember that these experiments were done even 100 years before, more than 100 years. So alpha particles, they are coming. They are 4 times the mass of hydrogen atom. They're quite heavy. So collimated, then pass through a small slit, fall on the gold foil, and the scattered ones now, they are caught on a zinc sulfide screen. Because whenever any charged particle will fall, zinc sulfide would give out light. So this was the idea behind this experiment. So now if you think of it as a plum pudding model, then the experiment results could not be explained. Therefore, Rutherford imagined for the experimental results. So let us go to the next one. So what is in that box now called the atom? So what is in that box? We don't know now. It is like a black box. See, when he did that experiment, it was like a black box. So he did not know what was there inside. So if all the mass was soft, then what would happen? When an alpha R is all the mass like ball bearings, hard. So this is the gun now, alpha gun. So you shoot randomly. Soft means without much reflection. If everything is soft, if everything is hard also, it will go. But only occasionally it encounters with a ball bearing, then it will be deflected by a large angle. See, this is, in your imagination, you are playing. See, this experiment has come. Some of the alpha particles, very small deflection. Some of the alpha particles, very, very large deflection, almost backscattering. And most of them passed undeviated. So most of them undeviated. Very small number, small deflection. Again, very small number, very, very large deflection. So now our imagination. So how the model should look like. So positively charged dense nucleus, negatively charged orbiting instead of embedded orbiting. Then now you can imagine most of them in between is all empty space. Therefore, when an alpha plum pudding means no way for alpha to scatter for at wide angles. But if it is like this, then you can see that the most of them, because between the positively charged center and the negative charged particles, there is almost empty space, therefore no deflection. And if in case if an alpha particle goes near the negatively charged particles, small deflection, because negatively charged particles, remember, their mass is very small and their charge is 1, whereas that of the alpha particle is twice. But in case they go near the positively charged mass, because gold means it has a lot of positive charges, therefore there is a large deflection. So this imagination now works. So this model now works because we haven't seen that, but this model, it is able to explain all the thing. That is why Rutherford model now. He calculated what is that itself would be the beginning of nuclear physics. He calculated what should be the size of the positively charged ones, where most of the mass of the atom is concentrated, and that was about 10 to the power of minus 14, and altogether it is 10 to the power of minus 10. Therefore, he understood now this model. So, planetary like model he imagined. So, same way, he imagined that in a planetary model, planets are going around the sun because of the gravitational force of attraction. And here he imagined that it is electrostatic force of attraction. So that is balanced by the centripetal force. So they are able to go, and all his experimental results were more or less explained. Therefore, Rutherford is considered the father of this modern atomic model. So it is not, of course, it is not up to scale. Okay. So even though it has almost 99.9% mass of the atom, it is very, very dense. So he now the name is coined. The positive charged center is known as the nucleus, and then cathode rays were named as electrons. So now this is the nuclear model of the atom. So, what is the relative scale? So, you imagine the atom size is like an outdoor football stadium. Imagine this is the atom. And what is nuclear size? Like a golf ball which is at the center. So, you imagine that you have kept the golf ball at the center, and that would be the size of comparison. Okay, so that big is the nucleus, and that small is that big is the atom. Very sorry, that big is the atom, and that small is the nucleus. But remember, 99.9% of the atomic mass is at the nucleus, that is at the golf size. Okay, in comparison only. Don't imagine that it would be golf size. It's never, it is a comparison. What is the ratio of size of atom to that of the nucleus? But controlling all the mass is there. Okay, and it has all the positive charges in that. So nucleus is like this. So this is the classical theory. This is known as the classical theory now. Rutherford's model. Remember, electron is a charged particle. It is orbiting around the nucleus. A charged particle, classical theories tell us that they are accelerating because it is going in a circular orbit. Therefore, it is accelerating. And any accelerated charges, it can be shown by electromagnetic theories that it will radiate energy. So, if it radiates energy, then what will happen? The electron will lose out its energy, then its orbit will become smaller and smaller, and finally it should fall into the atom. Say, for example, if the gravitational force exceeds from the sun, then the Earth's orbit would become smaller and smaller, and finally it will go and fall on the sun. But that is not happening because it is balanced by the centripetal force. See, they are equal. So here also, but accelerating electrons, if they are radiating, then finally they will go and fall. But that is not happening because atom as a whole is very stable. All the atoms that we see around us, they are very, very stable. This is not happening. Therefore, the next thing is Rutherford model might not be, even though it is explaining all the results, it may not be correct. Therefore, what shall we do? We will slightly, can we alter this model? So this is what, so Rutherford's model should only survive for 10 to the power of minus 12 second pico. So that means, but it's not so. Atoms are very stable. They are living forever almost. Okay? Especially gold atoms. You can see that they are living. Only some atoms, may not be. But most of the atoms are very, very stable. Therefore, then Rutherford's friend and almost his disciple, you could say, Niels Bohr, he made a very bold decision at that time. At that time, there were many discoveries as well. Solar spectrum was there, but there were some missing lines. So Fraunhofer had discovered this. Like low pressure gases do not radiate, in a continuous way. Black body gives continuous spectrum, emission spectra. But some of the gases at low pressure, they were not giving continuous spectra. In fact, they were giving discrete spectra. And photoelectric effect was there at that time. So, hydrogen spectrum, it was matched. The missing lines in the solar spectrum was matched with the some of the hydrogen lines. So, all these things, led Bohr to give a, improvised Rutherford's model. So, what he did, he retained because the Geiger-Marsden experiment, that was a beautiful experiment and it was never wrong, that experiment. It was repeated many times and it showed consistently, it showed the same results. So Rutherford model was able to explain all these results very well. Therefore, now that he had to think, but he had to show that it is a very stable one. Therefore, what he did was he made some bold assumptions like stationary orbits. That was the thing. See, at that time, Bohr did not have any, experimental or any theory to prove his point. But he made an assumption. See, this must be so. So there must be stationary states, and as long as they are there, they will not radiate energy. So what was this? So radiationless orbits. So he introduced this concept of, so he showed this. He introduced radiationless orbits. So what is that now? See, there was, what is the basis, you may ask? But there were no basis at that time. But atoms are giving out spectrum also. So when an excited atom, that is how the spectrum is coming. So his was radiation occurred only when an electron made a transition from one stationary orbit. What do we mean by stationary orbit? Where it was when it was there, it was not accelerating, or you could say that it was not radiating anything. So only when it goes from one stationary orbit to the other, when it makes a transition, it gives out a photon. The other way is also correct. It can also absorb a photon and it can go from one allowed stationary orbit to the other allowed stationary orbit. So this was a very bold decision of Bohr's. So see, he has kept same idea as that of Bohr, Rutherford, same idea, but only when they make a transition, absorbed or the emitted. So absorbed, it will go to the higher orbits, and emitted when it comes from a higher energy state to the lower energy states. So that means the orbits are arranged in such a way that they are all going from high energy states to lower energy states. So this was his imagination. So see, so this was his imagination. Okay. So when it goes, it will give out, or when it absorbs, it will take. So this is the Bohr's atom. So when it is in stationary orbit, you can see that it is not radiating anything. So that was the problem with Rutherford's model. So is there any basis, you may ask? Yes, there is. It will come after some time. Okay, after some slides, it will be there. But now let us look. So Bohr's model. So what he imagined that whenever when the boards are there, usually it will be in the ground state. That is the lowest energy states. It will be there. And all the other higher energy states, they are known as the excited states. And when it goes there, it will be, they are less stable, obviously, because excited states are all less stable. So it always makes an attempt to come back to the ground state. See, all of you, when you get angry, you go to an excited state. But the thing is, you cannot be there for long. So you will scold someone or you do something and you will come to the ground state. So more or less atoms are also like that. So you can imagine like that. Okay. See, even when we are very happy also, it seems we cannot be in that state because that is also an excited state. We always want to be in an equilibrium state. See, that is how nature is. So, then what is the criteria? How do you decide? What are the allowed states? How do you decide? So, Bohr decided that he found somehow, see, he had an intuition. Remember, Bohr had a very big intuition. So he imagined that these stationary states, see, these are all the postulates will come, many postulates. The important two postulates are this stationary states, three, you could say. So Bohr's model, stationary states. Then angular momentum. Anything that goes in an orbit has angular momentum. From classical physics, we have learned. Okay. So that means the orbit would be, it will be directed. So that is the angular momentum would be there. So that should be an integral multiple of h divided by 2 pi. H is known as the Planck's constant. H is a constant. So any orbit which, when the angular momentum is an integral, that means it can be h by 2 pi, 2h by 2 pi, 3h by 2 pi, 4h by 2 pi. So integral, no 2 pi into divided by 2 pi. So that is not allowed. So this is, so that means now it is quantized, like steps. Okay. So even in an escalator, you have steps. One small height is there. So no smooth. This one is not there. So it will go in steps. So that is the condition now he put. See, not all orbits are stationary. So, and what is the other important one? The difference between the energy, I will come to that. So this is the angular momentum is nh divided by 2 pi. M is the mass of the electron. V is the velocity in that orbit. R is the radius of that orbit in which it is going. H is Planck's constant. And N is a positive integer. That is very important. Okay. So When an atom is in one of these states, it does not radiate, but it will when it goes from one to other. So delta E, so the energy of one state, let us call it as En2, another, so minus, sorry, it is minus. It has come out as equal to all of you, En2 minus En1. So that correction I will make afterwards. Okay, En2 minus E1. So what are the postulates? An electron jumps from higher energy state to the lower, it emits radiation. So that is known as one quanta. And if it goes from a lower to higher, it will absorb. And that energy released, if the electromagnetic spectrum is there, it is from gamma to radio waves. If the energy falls, the emitted energy is in the visible region, we are able to see it as a visible spectra. We can see it as ultraviolet spectra. We can see it as radio waves, etc. We have not observed any atomic spectra in X-ray and gamma radiation region. Okay, so ultraviolet up to radio waves, so they will fall. Visible is there. Of all the known atoms, from ultraviolet up to this, it is there. So this is the postulate. Delta E, E2 minus E1 is equal to HF. So the important postulates, stationary states, the condition for the stationary states, MVR is equal to NH divided by 2 pi. And the third postulate, delta E, when it makes a transition, the energy E2 minus E1 is equal to HF. So this is the thing. So this is the Bohr model of the atom. But now, what the thing is, we have to find, see what we have measured. We have measured the hydrogen atom spectral lengths. We have measured. Now we will start with the Bohr's atomic theory for hydrogen-like atoms. What do we mean by hydrogen-like atoms? Which have one electron in their outermost, in their shell, orbit. Oh, then only hydrogen, no? Only one. No, it need not be. See, hydrogen's isotopes like deuterium, tritium, they also have one electron in their orbit. Not only that, a singly ionized helium. So, helium has two electrons. So, if you remove one electron, then it will be like hydrogen-like atom. Hydrogen-like, only one electron. So, he did for one electron in the orbit atoms. Okay. So, you can take for lithium. So, you can say that it is doubly ionized lithium, triply ionized. Like that, you can proceed. But of course, it becomes more and more difficult afterwards. So easier. So the isotopes. So you may be wondering, will deuterium and hydrogen, will they have different spectra? Definitely they will have some differences. Okay. So now what is that? See, Bohr, what he did was, he used quantum conditions and classical conditions. He used both. So what was his? Now we are going to get the spectral series that has been measured. The hydrogen atom spectral spectra, the wavelengths have been measured. So now theoretically, is Bohr's atomic theory going to predict that? Then we can say that Bohr's atomic theory is successful one. See, it should be able to explain the experimentally found results. So for that, what he did was, first of all, E2 minus E1 is HF. But frequency is velocity divided by lambda, you remember. Therefore, we are able to determine lambda. Therefore, our aim is to find the energy of the orbits. So that is our first aim. So for that, what we do is, Rn we call, let us say that the electron can be in any one of these orbits. It need not be in the ground state. It can have gone to the excited state also. So that orbit radius, Vn is the velocity of the electron in that orbit. En is the energy in that state. Mass of the electron 9.1 into 10 to the power of minus 31 kg. Z is atomic number. So actually now you understand that the atomic number is actually the number of protons. And K, that is a constant 1 by 4 pi epsilon naught. That turns out to be 9 into 10 to the power of 9. Newton meter squared, Coulomb to the power of minus 2, SI units. H is Planck's constant, 6.7 into 10 to the power of minus 34 joule second. Remember, Planck's constant has the same because it is the same as angular momentum. Then velocity of light, 3 into 10 to the power of 8, Rydberg constant, which we will be requiring. Electron charge, 1.6 into 10 to the power of minus 19. So these are some of the constants that we would be requiring. So what he did now, Bohr, he used the classical theory now. You can see that. What is that? The centripetal force, the necessary centripetal force. So it is going. It is balanced by the electrostatic force of attraction. So that 1 by 4 pi epsilon naught is written as K here. So ZE squared. So you remember, ZE is the charge of the nucleus and E that of the electron. So it has become ZE squared divided by Rn squared. So the distance is the radius of the orbit. So in one of the previous slides, we have shown. Now, what is Bohr second? This is the the second one is the important one. That is the quantization postulate. Because you have made that it cannot have any angular momentum, but it is nh divided by 2 pi. So here classical and quantum mixing now in Bohr's model. Rutherford only classical, but now the quantum, already Einstein was very successful in explaining photoelectric effect. Therefore, this has become very successful. Now what we do is, you can solve for radius using these two. It is algebraic. So what you will do now, for half mv squared, here mv is there. So you can substitute it here and you can determine what is the radius. Now you can see that radius also has become quantized now because n has appeared. So that is an algebraic. I have not done this, but I am sure that all of you can solve for these things. It is algebraic, this one. Okay. So there is nothing like that mv squared. You can write this as mv into v, and then you can write for mv from this one, and you can get first a v, and then you can substitute and get for Rn. So anyway, you can do it. So in fact, solving for Vn is very easy. So that also you can do. So these two, first it was done. Now this is written hydrogen-like atoms. See, if hydrogen only we had taken means Z will be 1. But suppose we take helium, then it would be Z would be 2. If we take lithium, it can be 3. So like that. If we take beryllium, it can be 4. So like that, one can do. But remember, only one electron in the orbits. So you have to ionize. Whether helium, lithium or beryllium, you have to ionize them. Right? Okay. So now this is there. So now you will be wondering, we have only M here. So will it not be the same for hydrogen, deuterium and tritium, its isotopes? Later on it was shown that instead of only mass of the electron here, one has to take a reduced mass. But anyway, you remember that for correctness sake, I'm telling you that all the that will be the drawbacks of Bohr's model. So he took like this. That is why. Now we can group all these constant things. So that turns out to be 0.53 into 10 to the power of minus 10. What is this? N is a variable. Z is a variable. N squared by Z in terms of meter. SI unit. So it is written like this. Or one can write it as 0.53 n square divided by z angstrom. So this is the radius. All right. Okay. So that constant is there. That is why for hydrogen atom in the ground state, when n is 1, z is 1, it is 0.53. So if you can remember this, you can determine the radius of any of these hydrogen-like atoms. Velocity turns out to be this. 2 pi squared k me squared divided by nh z. Here also one can write it as some constant times z by n. Okay, so in which orbit, how fast the electron is going. So this can be done. So next thing is, once we have this, we have to determine its energy. Remember, our aim was to determine the energy. So what is that energy? It is going in an orbit. And since it is in the electrostatic field of the nucleus, it has potential energy as well. So because of its motion, it has kinetic energy. So as usual, it is half mv squared. And this is the electrostatic potential energy. So minus k Z squared, the charge divided by Rn. So by substituting for V squared from the previous slide, you remember from this, one can show that this turns out to be minus half kZe squared Rn. Remember, k is 1 by 4 pi epsilon naught. Therefore, we substituted for Rn from the previous slide here, and it turns out to be energy is this. So one can write this in a simple way in terms of electron volt. See, you can write either in terms of joule per atom or in terms of electron volt. How do you get from joule to electron volt? You divide by the charge of the electron. So you will get it in terms of electron volt. So you can see that this is the energy. Oh, nothing to worry. 10 to the power of minus 18 is a very small number. But remember, atoms are all in a collective way. Therefore, it can turn out to be a huge energy. So don't be imagining that one atom only this much. So minus 13.6 z squared by n squared for all hydrogen-like atoms. So this is the energy. So you just substitute for z, you substitute for the orbit, n is equal to 1, 2, 3, etc. You will get. This is the energy obtained. Oh, now we are very happy. So we are very nearby. So hydrogen energy levels now. So when n is 1, n is 2, it makes a jump from 2 to 1. So in the previous slide now, when it is 2, you can calculate. Let us say that it is hydrogen only means Z. You can calculate what will be the energy in electron volt. And when n is 1, you can calculate it will be minus 13.6. And when n is 2, it will be minus 13.6 divided by 4. Therefore, it will be level 2 to this. The jump will occur. And you can calculate the jump is equal to HF. HF means HC by lambda. So you can calculate what is lambda. So you will be very happy to know that lambda, he predict whatever was the prediction from Bohr's atomic model was very close to the experimentally measured values. So Rydberg had done all this. See, he had done this. So minus 13.6 minus 3.4 to minus 13.6. So minus 3.40 minus of minus 13.6. Therefore, it turns out to be 10 point something, and one can calculate what is the lambda. And the Rydberg formula had given whatever how hydrogen wavelengths could be predicted experimentally. You know, empirical formula was used to give out experimental results, and both of them matched. That was the most important thing. And so now the question comes, what makes Bohr's allowed energy levels allowed? You know, that is a very important thing. So what makes it allowed? Okay. So 1 second. So what makes it allowed? See how the stationary orbits. Suppose when waves are in confined spaces. See, all these optics will give us ideas. They are in confined spaces. See, necessarily the nodes have to be at the ends and the antinode has to be at the center. If it has to get, a wave has to be within confined space. An orbit is a confined space, remember. So, in this way also it can be a node and in between a node, or it can be like this, many nodes can be formed, or it can be like this, so any number. So like a pattern now is emerging. So only those wavelengths that just fit in survive. Others cancel out. So this gives an idea about the stationary orbits. So our de Broglie dual nature of matter. So if they are not unable to fit in, then they cancel out. Destructive interference, they will go away. But it will destructively and cancels out. So that is why it is not stationary waves are not formed. But if the circumference is exactly the integral number of wavelengths, then they constructively, and this is because of the dual nature of matter. This result was, see, even though Bohr, intuitively knew about these things, he never thought electrons as waves. But de Broglie's dual nature of matter was able to explain the concept of stationary orbits. So this is how they were, Bohr's allowed energy states correspond to those orbits that are integral number of wavelengths. So that is why is equal to that stationary orbits. Now, we have got the proof for Bohr's assumption. It is now no longer an assumption now. So these are the Bose orbits. You can see that how a standing wave patterns has been formed. So that is there. Now the circumferences, suppose a circle you have moved. So how n is equal to 1, 1 wave. So n is equal to 2, 2 waves. N is equal to 3, 3 waves. How they are. Okay. So bonding. So like this. But then, of course, using very briefly, I will go through Erwin Schrödinger's wave equations. So he took the case of dual nature of matter and he wrote, this is for further study. So even though Bohr's atomic model was successful in explaining, it had its own drawbacks. Many drawbacks it had. Therefore, what Erwin Schrödinger did was he wrote a wave equation for electron. See, you had the light wave equation, which was written by Maxwell. Pressure sound wave equation we have written. So similarly, Schrodinger wrote an equation for electron. So this was the nature. It was a second order differential equation, which you have not studied probably till now. Maybe you have done only first order differential equations, but he was able to do that, get all the energy levels. Don't worry about these things, but I am showing you the beauty of mathematics in helping or in expressing the physics results. See, your thoughts are there, but you should be able to express it, isn't it? That is why languages are there, whether it will be sign language or it is a dance or it is English or Kannada, whatever it is, some expression should be there, isn't it? So, mathematics was the expression that gave for this physics. So, that was expressed. So, I'm going quite fast in this way. So, this is the hydrogen atom. So, quantum mechanical atom. Bohr's idea was this. But now everything is a probability. So that is the quantum mechanical atom. Okay. So now I would like to, for a moment, stop at this point and ask you about any interactions you would like. at this position. Then we can go for problems. That is not a. Let me stop the okay. Can anybody want to ask anything?
Thank you, madam. I request all the students, if you want to speak to madam and clear your doubts or any questions if you have in your mind, you can discuss with madam and get clarification for them. Please raise your virtual hand. We can unmute you. You can speak directly. Otherwise, you can mention in the chat box. Let it be an interactive session.
You can do one thing also. If for these questions, I don't want any answers as such. If you are able to give answers also, that is fine. Or you can give want to ask also, it is fine.
So students can interact by typing in the chat box as well as or raising their virtual hand. I will unmute them. You can speak. Try to answer for the questions as madam is telling. Any questions? Any doubts?
Okay.
Or any answers you would like to mention? Just mention
First
the
one.
options are either A, B, C, D like that.
The first one, it is a very simple one. Where in the electromagnetic spectrum would the Lyman series fall for Z is equal to 2 and Z is equal to 3? Z is equal to 2 means it would be helium atom. And Z is equal to 3 means it would be for lithium atom. Energy you have seen. See, we will go for the energy one. You can
No response from the students. Request all of you
students.
to please respond. It will be helpful for you only. Madam has taken a lot of efforts in preparation of this session, and see the presentation, the way she has put a lot of efforts.
Okay, see, you can see that this is the energy. So Z is 2 means so much of energy would be there. Z is 3 means so much of energy would be there. Okay, and let me give you a hint. Will it be in the ultraviolet region, visible region, or in the infrared? Anybody who wants to give?
At least type in the chat box whether it's right or wrong. Do not hesitate. ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಟೈಪ್ ಮಾಡಿ ನಿಮ್ ಪ್ರಶ್ನೆನ ಕೇಳಬಹುದು. ಇಲ್ಲ ಉತ್ತರ ಹೇಳಿ, ABCD ನಲ್ಲಿ ಒಂದು ಆಪ್ಷನ್ ಮೆನ್ಷನ್ ಮಾಡಿ.
Okay, it's okay.
Madam, there are some responses are coming now.
Okay,
ಈಗ
okay,
ಚಾಟ್
fine,
ಬಾಕ್ಸ್
fine.
ಅಲ್ಲಿ ಮೆನ್ಷನ್ ಮಾಡ್ತಾ ಇದಾರೆ.
Right.
ಅಲ್ಟ್ರಾವೈಲೆಟ್ ರೀಜನ್ ಅಂತ ಒಬ್ರು ಮೆನ್ಷನ್ ಮಾಡಿದ್ದಾರೆ.
Yes. How did you decide that it is ultraviolet? Correct. It is correct. For Z is equal to 2 because for hydrogen itself, the very first one would be in the ultraviolet. Very nice. Very good. Okay. For the second one, anybody? Okay, at least this one, fifth one. Anybody can answer. The energy of a hydrogen atom is positive. True or false? Fifth one, very simple. Yes, that is also fine. Okay, it is negative. Can anybody tell me or right why uh, why do we say that the energy of hydrogen atom is negative? See, if you go through, these questions are devised only for to test your see this one, whatever you have written is correct, but the thing is, it would be even better if you can write it as it is a bound system. So, for any bound system, the energy is always negative. So, that means you have to supply energy from outside to break it. So, remember these things. Any bound system has negative energy. Okay, so that is the better way to express. Okay, then the other ones, you can see that the second one is very easy. What is the main postulate of Bohr's atomic model? Circular, elliptical, straight lines. So which one? A, B, C, D. Electrons move in circular orbits. This is Bohr's atomic model only. In fact, there is what is known as a Sommerfeld model in which he takes elliptical orbits. That is there. Now, what is the radius of first orbit of helium atom? I had given one. See here. You need not try to do any this one. See, we can go to this. See here. 0.53 n square divided by z. So, for helium means you have to put our second orbit means this will be 4. So this necessary, just you put the whatever is that orbit number and the z number. So you will get immediately. So you need not worry and try to calculate. Okay. So this is how you have to calculate. Even in your multi MCQs also, multiple choice questions also, you have to see. So you just have to write first orbit means n is 1 and z is 2. So yes. So you can write yes, correct. So you can see that helium atom first orbit is smaller. You can see that. Bohr's model couldn't explain Zeeman and Stark effect. False, true. Yes, very good because it was unable, that was a drawback because it was very good from Ananya. Very good. So Ananya, Lakshmi, Nikhil, all of you are answering very nice. So it is correct. Splitting of energy levels he was unable to explain. Therefore, quantum mechanical model. What is I omega? Can anybody tell me? Yes, very good. So this one also you can calculate. See, these are very simple questions just to test your understanding immediately. So which was asked. And I thank everyone now. I will stop the screen sharing, and I am very happy for this opportunity. So it gave me, and if and students also answered, so that is I'm very very happy about that. And I once again thank all the people involved in KSTA for helping me in this presentation. Thank you very much.
Thank you very much, ma'am. At the outset, I would like to thank you very much once again on behalf of AST and on behalf of all the participants today here with us in this platform and those who have joined with us in the YouTube channel.
Mm.
Thank you. Thank you once again.
Thank
Such a
you.
wonderful presentation and brief. Yeah, the way you have put a lot of efforts in presentation, ma'am, animation
Thank you. Yeah.
and the graphics you have
Yeah.
used is very wonderful, ma'am.
Thank
It
you.
made all the students as well as us to understand once again the basics, how it works. Thank you
Thank
very
you.
much, ma'am.
Okay. Thank you.
Also,
Thank
I
you.
would like to
Okay.
thank all the faculty, teaching faculty, non-teaching faculty, and students who have joined with us today. Thank you. Thank you very much. Now, if you have any questions, you can mention in the chat box or ask us later also in the WhatsApp channel or WhatsApp contact number. So we'll get back to you with the answers. Meanwhile, we expect all of you to join on 4th of 3rd of the October. The session will be starting on 3rd afternoon at 4 o'clock. Thank you. Thank you very much, ma'am, once again.
Okay. Thank you. Okay.
Thank you, ma'am.
Bye bye. Bye bye.
Ma'am, we will conduct one physical program here in our campus once.
Yes.
It will be
Yes.
helpful.
Yes.
So, other than this, the more interactive it will be, the helpful
Yes.
for students them itself.
Yeah. Yeah. I will be very happy.
So,
I will be very
so
happy for
I request all the
physically.
students also
Yes.
henceforth, please try to respond and try
Yeah.
to speak to
Yeah.
the speakers. You will be given a golden opportunity to
Yeah.
speak such experienced faculty where you will not be able to speak to them outside this KSTA channel. So make the best use of this platform and try to speak to them and get clarification of your doubts and queries related to the curriculum. With this, today I would like to conclude
Okay.
formally once again thanking all of you. Thank you.
Thank you. Thank you.
Thank
Bye
you.
bye. Bye bye.
Bye. Bye.
Bye.